The quiet village of Daresbury near Warrington is the birthplace of Charles Dodgson. Under the pen name of Lewis Carroll, his famous children's book Alice's Adventures in Wonderland made him a household name. But even Lewis Carroll's fertile imagination would never have dreamt up what now lies just a field or two from Daresbury village. Sitting beneath a giant experimental tower in the Daresbury laboratory is a particle accelerator named after Lewis Carroll's heroine, and is one of the most extraordinary machines ever devised. In this strange world, Alice now becomes the initials for accelerators and lasers in combined experiments. Alice is a machine capable of entering a completely new realm of miniaturization, expanding time to unimaginable lengths and cavorting with electrons as they dart around molecules. Alice is one of the jewels in the crown of STFC, the Government Science and Technology Facilities Council. Alice is a technology demonstrator for accelerator and laser science and is the first of its kind in Europe. And within a year of operation, it's already produced advances in medical research. Daresbury Laboratories Cockcroft Institute is the powerhouse behind Alice's design. Professor Susan Smith is the head of Daresbury Laboratory and is particularly excited by the shortness of the light pulses produced by Alice.
The shortness of pulse is very important because if you can get that shortness, then you can actually start to look at processes at a minute level.
One of the team working for a decade to perfect the shortness and intensity of the light pulses is Dr. Lee Jones.
Well, in a chemical reaction, the dynamics are taking place on a femtosecond timescale. So this is extremely short, very, very, very rapid dynamics.
We're looking at what we call 500 femtoseconds. If you consider the speed of light, this is the time it takes light to cross a hair. That's how fast it is.
If we were to scale one of those pulses up to last for 1 second, then a real second would last something of the order of 16,000 years.
But this astonishing ability to flash the briefest moments of time is only half the battle.
Taking still shots can be quite clear, but it tells you nothing about how things work. If you start to take movies, then you start to understand processes.
This principle is well illustrated by the mystery of how a horse gallops. Before the invention of the movie camera, this is how it was depicted: legs out the front and legs out the back. The moment the first movie was taken, the subtleties of the action became apparent.
The elegance and the dynamicism of the muscular movements of horses was truly revealed. And that's a sort of revelation that can be seen as you dilate and slow down time, and that is what Alice is at the forefront of.
This is a simulation of the pump-probe process, which is the source of Alice's movies. A sample, say, of a prospective new semiconductor for improving solar panels is the target. A flash of light from a laser is fired at it. This is the pump. It's absorbed by the sample's electrons, which enter an excited state. A moment later, the excited sample is hit by photons from Alice's accelerator ring. This is the probe. The small amount of this light that is bounced back reflects the amount absorbed by the electrons, which in turn is a measure of the electron's excitation. The pump residual light enters a detector, which measures its intensity. By changing in 500 femtosecond steps the arrival time of the probe photons, a movie of the probe's residue intensity is created. And it's these blips that are recognized by physicists as characteristic of particular electron movements. So how does the Alice accelerator ring, recreated here in virtual reality, actually work? A cathode is flashed by a precisely timed green laser, and tightly packed bunches of electrons set off in an acceleration lane, firstly through an 8 million volt booster and then through a series of bending dipoles. Here they're coloured blue, and a series of focusing electromagnets. As they approach the speed of light, they are ready to join the ring where they enter the energy recovery linac. Stripping this down in virtual reality shows its complexity. It's the only one of its kind in Europe. Here, the electrons surf on waves of electromagnetic energy before being catapulted off round the ring. The electrons travel just once around the ring before recycling their energy in the same energy recovery linac. But how do all these tight bunches of speeding electrons produce Alice's unique flashes of light? These electrons are travelling in a straight line through a switched-off electromagnet. When it's switched on, the magnetic field forces the electrons to bend. It's a fact of nature that forcing electrons to change direction causes them to dump some of their energy as photons of light. And if that's not enough, the electrons are forced to slalom round a whole row of magnets.
We make them wiggle. We put them through a wiggler. And as they wiggle, they undergo an acceleration, a quick change of direction. And this creates, through relativistic processes, a short pulse of light.
This is known as synchrotron radiation, is the technical term, but if you want a simple analogy, simply the beam shines.
Alice is now up and running and has already received its first scientists anxious to use Alice and its wiggler, called a free electron laser, not only for its brevity of pulses, but also for its ability to produce infrared radiation. Professor Peter Waitman from Liverpool University has already hit the headlines with breakthrough cancer research.
The previous work on a synchrotron indicated that if you had much higher power levels, the sort of power levels that we have on Alice, it would be possible to develop a way of diagnosing esophageal cancer. What we are doing here is looking at specimens extracted from people's esophagus, and we're looking at it with a very powerful microscope which operates in the infrared. And this only works because we have a very powerful infrared free electron laser.
And it's the tunable, minute accuracy of this laser's output that enables the making of chemical maps of the material inside a cell's nucleus. Showing up in red here is this cancerous cell's distended DNA, revealed by absorbing a precise infrared wavelength. This benign cell shows a normal, healthy amount of DNA. Terahertz radiation is increasingly being used for security at ports of entry. Here it penetrates a lorry's side wrap to reveal concealed cars. As plans to expose humans to this radiation are being contemplated, Professor Waitman is using Alice's ability to produce such radiation at ultra-powerful levels to investigate its properties.
Terahertz is very penetrating radiation. It can pass through brick walls, clothing. You're able to see people without their clothes on and see if they have concealed weapons. And the first aim of our research program is to establish the safe level of human exposure to terahertz radiation.
We can irradiate live cells and check whether this radiation is doing any damage to those cells.
Alice has enormous potential for research in a large number of fields. It can be used to work on solar cells, photovoltaics. It can be used to look at nanoparticles. It can be used for fundamental work on the structure and orientation of molecules.
As the list gets longer, Alice, as a demonstrator, has shown how effective this type of accelerator is, and it's also allowing its operating team to explore what a future large facility for life sciences should look like, including widening its spectrum into the X-ray band.
It's important that British industry is at the absolute cutting edge to keep surviving. What Alice does is gives them the products of the future that will allow them to compete.
Alice owes her name to the fact that Daresbury is the birthplace of the writer Lewis Carroll. Alice in Wonderland was centred on distortions of time and space and size and scale. And that is really what we're achieving when we operate Alice. I think it's fair to say that what we do here is we open the gateway to Wonderland.